Hi. In this lecture, we shall discuss another application of the Gauss law. Okay. We shall start with Gauss law. Using Gauss law, we can find electric field intensity at a particular point. To find electric field intensity, Gauss law gives us electric flux density D. And this electric flux density is given by integral form of Gauss law, that is closed surface integral of D over a closed surface. So we know that this is the integral form of Gauss law, from which we can find D at a point due to a given charge distribution. Here, Q can be any charge distribution, need not to be point charge, any charge distribution. So given a charge distribution, we can find D, and from D we can find E. This is one of the very useful application of Gauss law. But the problem here is this integral form of Gauss law, which is on expansion, becomes integration of d ds cos theta. This integration is a closed surface integration, and this integration is performed on Gaussian closed surface. The complexity here is from the term cos theta and also the integration over closed surface. To reduce the complexity, you know that we choose either theta as 0 degree or 90 degree. These two angles of theta will make cos theta is either 0 or 1. So the three terms under integral sign become 2. But how to choose theta either 0 or 90 degree? That is by visualizing or constructing a closed surface, that is Gaussian surface, such that it is either normal or tangential to D. This angle theta is between the closed surface and D. The closed surface and D. If the closed surface is perpendicular to D, then theta is 0 degree. Otherwise, if it is tangential, it is 90 degree. So it becomes a condition to draw the Gaussian surface. It should be either normal or tangential. Otherwise, the complexity of this mathematics cannot be reduced. So after choosing properly, the theta, cos theta becomes either 0 or 1. Now in the second step of evaluation, we see to that D becomes constant in the Gauss law. To make the D constant over the closed surface, we have to visualize the closed surface symmetrically about the charge distribution. Then only D becomes constant. For example, if you have a point charge Q, then the closed surface or Gaussian surface to be constructed around the point charge must be a sphere having the charge at the center. Then the spherical surface becomes symmetric about the point charge, and D becomes constant on this closed surface. Similarly, if we have a line charge, then we visualize a cylindrical closed surface around the line charge. So that electric flux density on the cylindrical side becomes constant, that is D. On the top surface, it becomes 0. Bottom surface also, it becomes 0 because the direction of D tells that D is tangential to top and bottom surface, but normal to cylindrical side. So cos theta is 1 on the cylindrical side, and cos theta becomes 0 on the top and bottom surfaces of this closed cylinder. So likewise, by visualizing the Gaussian closed surfaces symmetrically around the charge distribution, we can reduce the complexity of integration in the Gauss law. So this idea tells that it is easy to use Gauss law to find D and E if and only if the charge distribution is uniform or symmetrical. If the charge distribution is not symmetrical, then visualizing the closed surface, imagining the closed surface or constructing the closed surface around the charge distribution becomes difficult. It becomes very difficult to maintain theta 0 or 90 degree. And also it becomes very difficult to take D as constant. So in a summary, if charge distribution is not symmetric, nothing but if there is asymmetric charge distribution, then the two conditions what we discussed just now may not be satisfied. That is, cos theta may not be always equal to 0 or 1. This will not remove the cos theta term from Gauss law equation. Secondly, D may not be constant. This restricts the use of Gauss law for asymmetrical charge distribution, which is not at all recommended because of high complexity of mathematics. But in this lecture, we shall discuss the possibility of using Gauss law for this asymmetric charge distribution. What we do here, if there is asymmetric charge distribution in the space, where the density rho, the charge density rho is not constant everywhere. If it is not constant, or if the charge is asymmetrically distributed, then what is advisable is to choose a smaller Gaussian surface of any shape, rectangular or spherical or cylindrical, whatever the shape it is. When the closed surface is very small in area, or if it encloses very small volume, let us say an incremental volume delta V inside any of these closed surfaces. If the volume is an incremental volume, then there is a possibility of maintaining D constant on these surfaces. So we can start working upon using Gauss law or applying Gauss law to asymmetric charge distribution by choosing an incremental closed surface or a small area enclosing a small volume delta V such that on the closed surface D remains constant. If we start this way, we may find some useful relation to address the problems of charge distribution. So let me start deriving an equation or derivation of Gauss law for this special case, right? For the special case, asymmetric charge distribution. After considering asymmetric charge distribution and after applying this closed surface of smaller volume, finally may give us one equation to find D, at a point inside that volume. If we apply the limit, if we consider the limiting case, that is the limit delta V tends to 0, then definitely we may end up with an equation for D at a point. Okay. So once again, if we consider a closed surface, a small closed surface enclosing an incremental volume delta V, and we apply the limiting case in the end, delta V tends to 0, then we may end up a useful equation for D at a point within that volume. So this equation later will be called as Gauss law in point form. Gauss law in point form or Gauss law in differential form. Differential form. It's called so because upon applying the limits delta V tends to 0, the volume delta V finally becomes differential volume dV, and the corresponding equation also called differential equation. And the volume element dV is later called differential volume element. And we can give an equation for D at that particular point. Okay. So in this discussion, we will do two things. One is we will derive an equation for Gauss law in point form. And also we discuss the application of Gauss law to a differential volume. Differential volume element. Differential volume element. These two problems will be addressed here. So we shall proceed this discussion by choosing an appropriate coordinate system. Here, I'm going to consider a rectangular coordinate system because under differential condition, the shape of the differential volume or incremental volume will not be a matter, because in differential condition, the volume surrounded by a small closed surface of any shape will be almost same. Just for simplicity, we shall start with a rectangular coordinate system. So now in this coordinate system, I'll consider a closed surface, rectangular in shape, enclosing an incremental volume. Okay, so this is going to be our Gaussian surface, imaginary closed surface. Gaussian surface is an imaginary closed surface, which is a rectangular box of volume delta V, incremental volume delta V. Let the three lengths of this rectangular box be delta Y, delta X, delta Z. The side parallel to Z axis is delta Z, parallel to Y axis is delta Y, parallel to X axis delta X, such that the incremental volume of this space enclosed by the Gaussian surface is delta X into delta Y into delta Z. After application of the limit, after applying the limit, this complete closed surface shrinks to a point. In the limiting case, the differential condition, the entire closed surface shrinks to one point. That time it may shrink to point here. Let me call this point as P. And the value of D we found on the surface becomes the value of D at the point P afterwards. And let that D value be D vector D. The electric flux density using Gauss law will be found on the closed surface. In the limiting case, the closed surface shrinks to the point P. Then the value of D on the closed surface becomes the value of D at that particular point. And also, just for clarity, we can also call this one DO, that particular point, which will be having three components of XYZ in this coordinate system, which can be further expanded as DXO, the X component, DYO, Y component, plus DZO, Z component. D being a vector will be having its own XYZ components. So here, let me summarize. I've chosen Cartesian coordinate system. The charge is asymmetrically distributed everywhere. I've chosen an incremental volume delta V enclosed by a rectangular closed surface with the lengths of the sides delta X, delta Y, and delta Z. And we have defined the electric flux density at the point P inside that closed surface. Right? What is the assumption while constructing this closed surface? It is assumed that first point, D remains constant on the rectangular faces. Rectangular faces. If D doesn't remain constant, then it's difficult to apply Gauss law. So keep the Gaussian surface so small such that D remains constant. D should remain as the constant on the surface. If not constant, further reduce the volume inside the closed surface. Keep on reducing till it becomes constant. First point. Second point is the theta value, that means the D with respect to closure. D is either normal or tangential to each face. Okay, D is either normal or tangential to each face. So that's how we have to visualize the closed surface. Now we shall start with Gauss law. Integral form of Gauss law. Integral form of Gauss law is available. That is the closed surface integral of D. That is the surface. And that is your Gaussian surface, which is equal to Q. What is Q here is? Q is the total charge inside the Gaussian surface or closed surface, otherwise is the total charge enclosed by the closed surface. In rectangular coordinate system, the closed surface is defined by 6 different rectangular planes. So we shall split the closed surface integral into 6 different integrals to carry out the derivation further, because all the 6 phases look in 6 different directions. So it's advisable to go separately for each phase. Now the closed surface integral of d dot ds will be having 6 integrations which are not closed, which are open. Each phase is an open phase. Okay, let us say we'll give the name for them also. One is front phase. Similarly, another one will be back phase of the rectangular box. The right phase, the left one, integration over top face and integration over bottom face. Let me declare this as equation number 2. We have 6 integrals over rectangular planes which put together will give us the closed surface. We shall consider each of these 6 integrals separately. Okay. Let us consider the first integral, which is taken over front face. In this case, we have to integrate d over the front face. The d over the front face will not be the complete flux. All the complete flux will not be available at the front face. Only some part of the flux will be passing through the front face. The remaining flux may be passing through other phases. So we have to evaluate that part of D, or the value of D on the front face, which is available at that particular phase. So we shall put a subscript F here to remind that we have to evaluate D only on the front face. Okay. Now, the ds, let us address the point of ds. ds is the differential area on the front face. If we just consider the front face of the closed surface separately here, this makes the front face. Other faces are not of our interest. This front face is a total area of delta y into delta z. And this front face is looking towards positive x-axis. That means the direction of the front face is positive x-axis. Any flux coming out of this front face will be moving in positive x-axis. If we choose small differential surface area, the ds here, then this ds will be having an area dy into dz. dy dz is the differential area taken over the incremental area of delta y into delta z. This dy into dy will be available on limiting case. So, in place of ds here, what we can write is dy into dz a cap x. So, the differential area ds taken over front face will be dy dz a cap x. It is a vector. In the next step of the integration here, the D vector is also having three components. It's a vector, it's having x, y, z components. So we can expand df as dxf ax, dyf ay, dzf az. So the vector D may be having three components, but our surface vector is only having x component. So this dot product gives us now dxf into dy into dz. Ax dot ax is 1, ay dot ax is 0, az dot ax is also 0. This says that the only x component of the D will pass through the front face. The y and z components being tangential to front face, they cannot pass through the front face. That's why we end up with only x component here. Next, according to our second assumption in the beginning, D always remains constant on the phases of the Gaussian closed surface. That's why in this particular case, the dxf will be taken outside the integral. Okay, then we have to integrate only dy and dz. So dy and dz can be separately integrated. Dy will be integrated over the limit of delta y, dz over the limits of delta z. Then finally, we will be having dy integration is y, applying the limit, total length of the side will be obtained, and this becomes dz. So the total integration is total length on each side. This gives us the integration of D over the front face dot ds. Now the question is, what is dxf? What could be this dxf? How to find this? So for that, we shall proceed in this way. If you consider once again the total Gaussian surface, let us say this is the front face and this is the back face. These faces are moving inside the plane of the paper. And this is the center point. At this center point, the flux density is D. And this distance is delta x. To understand this diagram, we may have to move back to the original picture. Yeah. So in this case, I'm looking from this side. Okay. So if you see from this side, then this line so this line, this phase and this phase we are concentrating, and this length between these two is delta x. Visualize this one. Visualize this one inside this. Yeah. Okay. The front face is there somewhere. This is our front face, and this is the back face. Okay, distance between these two is there. At the center point, D is here. And we know that only x component of D is passing through the front face. This x component value on the front face is dxf. The x component value at the midpoint is dxo, or simply dx, whatever it is, dxo. This dxo, by the time it comes to front face, it becomes dxf. And by the time it becomes to back face, it becomes dxb. The value of the D, flux density, changes from point to point. dxy, which was at the midpoint, becomes dxf on the front face, dxb on the back face, because the distance between them is some value delta x. Now the question is, when the dxo changes from midpoint to front face through a distance of delta x by 2, its value changes to new value. How to find dxf? Now that's the question. How to find dxf from the dx, from this dx? How to find this one? So we can think this way. Okay. What we want here is dxf, the x component of D on the front face. What we know is dxo, the x component of D at the midpoint. So what is the value of dxf? It depends upon the rate of change of D with respect to distance, because D changes from point to point. D changes over a distance of delta x by 2. If D is changing faster, then dxf becomes smaller, too smaller or too larger, depending upon is increasing or decreasing. That's why we can find dxf in this way by considering rate of change of the x component of D with respect to x. That means in x direction, what is the rate of change of dx? What I mean is the initial value of x component of D is dxo. From there it start changing with respect to distance in x direction. This is what is our rate of change of x component of D with respect to x. See, the numerator is change in D, denominator is change in distance. If you want to know what is the total change of dxo from midpoint to the front face, means the total change in distance is delta x by 2. So if you multiply this one by delta x by 2, see the denominator is change in distance. Delta x by 2 is also change in distance. After cancellation, you will get change in D. Delta dou dx is the change in dx from midpoint to front face. So this equation can be used here to find dxf, the x component of D on the front face. Actually, this same thing can be found using Taylor series. Taylor series gives us a function which is changing by small values. So here dxo is the first term of the Taylor series. First order partial differentiation is the second term of Taylor series. We have restricted ourselves to first two terms of the Taylor series. The third one comes with second order partial differentiation, which can be taken as negligible. Dou square dx by dou x can be neglected, assuming that the distance between the front face and the midpoint is very small, because the total volume is delta V, smaller volume. Okay, so we can bring this equation back to our original equation of the front face calculation. Let me call this equation 3. Now the equation 3 becomes okay. Now equation 3 becomes, that is the integral of D over front face. Becomes, now we're integrating the value of D over front face. Now it becomes, we can think of what is to be substituted. Now if you go back and see there, look at this term. What is supposed to be addressed here? So with this fellow, dxf into delta y into delta z. Delta y, delta z gives total area of the front face, which will remain same. So in place of dxf, so we can write dxo plus dou by dou x of partial differentiation of dx. So this is not a dot product, better to avoid dot, into delta x by 2. This gives us the value for integration over front face. Similarly, we can easily predict the value of D over back face, because the area of the front face and back face, the area of the front face and the back face of the Gaussian surface is same. Area is same. The distance from the midpoint to both the faces is also same. That's why we can easily predict. The only one change is the flux from the front face is in positive x direction. from the back phase is towards negative x direction. Okay, from here, flux move in opposite directions. So because of that, we can make a guess for second integral, that is similarly integration over back phase of the Gaussian surface can be taken as dB by dt is equal to what can be the answer for this now? Okay, here in this particular thing, we substituted only for dxf, and this also contains delta y into delta z. Okay, this can be evaluated in the same way. I'll give you the steps here just for confirmation. Okay, so how do we perform this one? This is going to be your regular dxb into the delta y into delta z becomes minus delta y into delta z, because the direction of the back phase is towards negative axis. In the dxb, that is the x component of d that is passing through the back phase will be moving in negative x direction. The x component of d here, the x component of d, let us say this is specifically dxo. This is going in negative x direction. For the front phase, it is positive x direction. Then the rate of change of dx into delta x by 2 will be same. Here it is minus delta y into delta z. Now, let us consider the algebraic sum of the flux passing through the front phase as well as the back phase plus the back phase. See, these two flux are passing in opposite directions. They get subtracted to produce the total flux passing through the closed surface. Therefore, so whatever the value we consider in the front phase and back phase, so in that one, let us look into that equation. Let us go back and find out what we got for the front phase here. Look at this equation. And we'll copy over this one too. Main equation. Yeah, both are available here. So the value what we got for the front phase, that is dxo plus partial differentiation of dx into delta x by 2 to delta y plus delta z. If this quantity is positive, then whatever the value we got in the back phase should be subtracted from the value of the front phase to get the algebraic sum. So then it's going to be minus dxf plus partial differentiation of dx into delta x by 2 to minus delta y into delta z. This algebraic sum gives us the equation here. This minus into minus plus dxo gets cancelled out in both the cases. So we are left with these terms, which are similar. So we can write them as 2 times dou by dou x of dx into delta x by 2 into delta y into delta z. So after cancelling the 2 from both numerator and denominator, so we are left with partial differentiation of dx into delta x into delta y into delta z, which can be simply written as delta v. So this equation I can simply call it as equation 4. This is the value we got after adding the flux passing through front phase and back phase, which are perpendicular to x-axis. Similarly, we can write the equations for the value of or amount of flux passing through the other 4 phases. Let us say through the phases right and left, we may end up with the value. So look at this one. In the first pair of phases, which are perpendicular x-axis, we have only x component. Similarly, the right and left phases of the Gaussian surface are perpendicular to y-axis. So that's why the answer would be dou by dou y of dy into delta v. This becomes question 5. Similarly, the other 2 pair, the flux through top surface and bottom surface is equal to dou by dou z of dz into delta v. This makes equation 6. So we have equations 4, 5, and 6, which are giving the total flux passing through all the 6 phases. Now we should substitute these 3 equations back to the closed surface equation. Let us find out which equation it is. Equation number 2. So look at this equation number 2. The left side, total flux passing through closed surface, that is closed surface integral of d. So in this equation, we have to substitute. Using equations 4, 5, and 6 in equation 2, so we get the closed surface integral of d is equal to, so consider all the terms, dou by dou x of dx into delta v. Delta v can be taken out as common factor. Dou by dou y of dv, dou by dou z of dz. The incremental volume is taken out as common factor. So the 3 partial derivatives are given by. Let us say this is equation number 7. But now if you consider left side, that is LHS of the Gauss law, but the closed surface integration of D is always equal to total charge enclosed by the closed surface. This is the Gauss law actually. Now from both the equations, from equations 7 and 8, we get one more relation, that is closed surface integration of D is equal to Q, which is also equal to partial differentiation of the components of D multiplied by incremental volume delta P. So we have three terms here which are equal to each other. And these three values give us some concept. But here, the idea is to avoid this closed surface, because the closed surface can only be a smaller closed surface. Otherwise, evaluation becomes difficult. Right. So that's why now we go to the next step. That is the limiting case, in which we try to reduce this incremental volume delta V to as small as possible. So we shall apply the limiting case. As a limit, incremental volume delta V tends to 0, and the volume shrinks to 0, that closed surface also shrinks to 0, then the volume within the closed surface becomes point P. Then mathematically, the limit delta V tends to 0, which is applied to the first term of previous equation, is equal to the limit also applied to the second term, that is Q, which is equal to the limit delta V tends to 0 for the last term. The three partial derivatives. But here the first and second terms do not contain the volume terms at all. The last term contains volume term. The last term in that equation, that is partial differentiation of D, contains delta V. So there is no relation between that incremental volume delta V and the rate of change of D. That's why we can try to bring that incremental volume to the first term, that is closed surface, because delta V is the incremental volume enclosed by the closed surface. It is more appropriate if delta V is introduced to first term. So that's why we shall go for one more step. If we divide throughout by delta V, the equation becomes as the limit delta v tends to 0. Now the closed surface integral of d to be divided by delta v is equal to second case also gets divided by delta v because we have divided throughout. Now in the limiting case, the last term does not contain any volume term. By inspection, we can understand that is not required for the last term. The first term and the second term have some meaning, physical significance after applying the limit and dividing by delta v. Particularly the second term, charge by volume, coulomb per meter cube, as the volume shrinks to 0, becomes volume charge density at the point P. Q is the charge inside the delta. Q is the charge distributed inside the delta V as the volume shrinks to a point. So Q by delta V becomes charge density. The first term becomes definition of divergence of D. This is the mathematical definition of divergence of a vector D. Therefore, now we can introduce new terms into first and second terms. The first term of the above equation becomes div D, nothing but divergence of D. This is a mathematical definition of the divergence. Similarly, the second term is the definition of volume charge density rho v. They become rho v. So these two interpretations are obtained from the definition. Whereas in the last term of the equation, if you observe carefully, in this term, we have to apply the limit delta v tends to 0, but in the terms within the bracket, there is no delta v at all. So the term is independent of volume. So the limit can be dropped here. So finally, we got a relation that is divergence of vector D is equal to rho v is also equal to partial differentiation of components of vector D. We have this useful equation. This relation can be used to find the divergence of electric flux from a point. We can continue for two more steps to get another equation by understanding the last equation. See here, rho v is a scalar. So divergence of D is also scalar. Both are scalar quantities. D is a vector, but divergence of a vector is a scalar quantity. Then the last term is also scalar. There are no unit vectors. But in the last term, we have the presence of D in component forms. So the last term contains D, complete D in component form. So if you bring back the vector form of D to the last term, we'll get one more useful equation, that is div D is equal to rho V. The last term can be expressed as a dot product of two vectors because D is a vector, but whatever the outcome we have is a scalar. D is multiplied with dou by dou x, dou by dou by dou, that is partial derivatives. So there must be two vectors in the last term. So keeping this point in mind, we try to define two vectors. First vector may be dou by dou x ax, dou by dou y ay, dou by dou z az. So this can be the first vector, which is dot product with vector D itself, dx dy dz in vector form. So if you perform dot product between these two vectors, we will get back the third term in the above equation. So here, the first vector in the last term, if it is denoted as an operator, del, this can be called del, which is basically mathematical operator. It's just a mathematical operator representing this partial differentiation. Then the second term can be denoted as vector D. Then finally, we get a useful relation del dot D. So hereafter, the term del dot D can be pronounced as divergence of D. So this equation can be used to find volume charge density, or we can take out the last two terms and make one separate equation. Divergence of D is equal to rho V. This is called point form of Gauss law. Point form of Gauss law. Because this is derived from Gauss law concepts as applicable to a point. Okay. No integrations are involved here. This is the very useful part of this equation. So we need to perform complex integral over here. But this equation gives us the value of electric flux density at one point. So using this equation, you can find flux density at any point throughout asymmetric volume charge distribution where no complex integrals are involved. So the divergence of D is equal to rho V. So this is the derivation. Thank you.